This is an overview of section 1.1, numbers, data, and problem solving. So the topics we're going to cover are identifying common sets of numbers, applying order of operation, PEMDAS to evaluating expressions, scientific notation, and some basic introductory problem solving strategies. We're going to start looking at some groups of numbers. We have to define and categorize things to begin with in mathematics. We have a group that's called our natural numbers, or we often refer to them as counting numbers, and these numbers are basically 1, 2, 3, 4, 5, and so on. They're called natural numbers because we naturally start counting at 1. A lot of times we'll identify them with the large letter N. There's another group which the textbook does not emphasize as much. It's called the whole numbers. These are basically your natural numbers plus 0, so your whole numbers are 0, 1, 2, 3, etc. The third category are integers, and integers are basically your whole numbers and their opposites. So they include 0, 1, 2, 3, and their opposites, which are negative 1, negative 2, negative 3, and so on. And a lot of times we'll identify this set by the large letter I. We have a couple other groups we want to look at. We have what's called rational numbers, and the root word of rational is ratio. When we think of ratios, we think of fractions. And rational numbers are basically real numbers which can be expressed as a ratio of two integers. We already talked about integers, are your positive and negative whole numbers. So I can take a rational number and express it as a ratio of two numbers, p over q, where q doesn't equal 0. The reason we require q not equal to 0 is because we can't divide by 0. So I can write it as a fraction. Some examples of the number 8. Well, 8 doesn't have a denominator. I can write 8 as 8 over 1. Another example would be negative 6. I can write this as negative 12 over 2. Or 0, I can write it as 0 over 5. Now these all seem obvious. These are our integers. So any integer can be written as a rational number, as a ratio of two numbers. But I can also include some decimals. I can take 0.25 and write it as 1/4. I can take 0.43 and write it as 43 over 100. And I can take 0.333 repeating and write it as 1/3. So basically, any integer can be written as a rational number. I can also take decimals and write them as rational numbers, and the decimal has to have one of two properties. The decimal must either terminate, in other words, it cannot go on forever. So our first two examples here, the decimal terminates. When I have a decimal that terminates, I can always write it as a fraction. Or the decimal has to repeat itself over and over again, like my example of 0.3 repeating. It can repeat more than one digit, like 0.425 repeating. Or it could have a first part that doesn't repeat and a second part that does repeat. So 5.16 that doesn't repeat, then the 2,3 does repeat. So if I have it either terminating or repeating, you can write it as a rational number. This gives rise to what we call our irrational numbers, and irrational numbers are basically numbers which cannot be expressed as a ratio of two integers. In other words, they're not rational numbers. They have decimals which do not repeat and do not terminate. Some common examples are pi, your 3.1415, etc. It never repeats itself. Your radicals are also common, like the square root of 3 does not reduce, the cube root of 11 doesn't reduce. Or you have numbers that maybe look like they make patterns like this, 0.03, 003, 003, 0003. In other words, I'm writing 3 all the time, but it's not necessarily repeating itself because each sequence has an additional 0 in it. And this gives rise to the last category we're going to talk about in this section, which are real numbers. And real numbers are basically anything that we've already looked at, anything that you can put on the number line. So how are all these numbers related? Well, you want to look at it like this. This is kind of a Venn diagram. If we think of this large outer rectangle, which includes both the orange and yellow part, this represents our set of real numbers. So everything we're going to look at is a real number. And within the set of real numbers, I have two groups. A group that's called the rational numbers and a group that's called the irrational numbers. And they do not overlap. However, within the rational numbers, I also have my integers. And within the integers, I have a group that's called the whole numbers. And within the whole numbers, I have a group or a set that's called the natural numbers. Now, the way this works is that if you're an integer, that also means you're a irrational number, which also means you're a real number. If you're a natural number, that means you also fall as a whole number, which also means you fall as an integer, and a rational number, and a real number. Let's see how we can categorize some of these. Let's classify each of the following real numbers. So I'm going to have a list of real numbers. And we want to classify them as natural numbers, whole numbers, integers, rational numbers, and irrational numbers. So I have negative 2, square root of 36, cube root of 27, 5.28, 0.15151515 repeating, 13 ninths, and radical 7. If I look at negative 2, we know it's not a natural number. We know it's not a whole number because it's negative. Therefore, it's an integer, which also means it's a rational number. If I look at the square root of 36, a lot of times we jump on the square roots and think they're irrational, but if I can simplify it, it's not. The square root of 36 reduces to 6. The cube root of 27 reduces to 3. So 3 and 6, these are natural numbers. They're also whole numbers. They're also integers, and they're rational numbers. The next three I looked at, the 5.28, the 0.15 repeating, and the 13 ninths. Remember, decimals that terminate are rational numbers. So are decimals that repeat. And 13 over 9, 13 is an integer, 9 is an integer, so this is a ratio of two integers, so by definition, it's a rational number. So all three of these are rational numbers. And finally, square root of 7, I cannot reduce that at all, therefore it is an irrational number. Let's talk about scientific notation. We can rewrite some numbers using, actually we can rewrite all numbers using scientific notation. I can take some number r, some real number. I can write it as c times 10 to the n. Well, n is just going to be an integer. It's going to be 0, 1, 2, 3, 4, etc., or negative 1, negative 2, negative 3. And I'm going to define the c to fall between 1 and 10. In other words, I want to find some number between 1 and 10 and multiply it by 10 to some power. Now the key here with c is there's only one non-zero digit to the left of the decimal place when I'm looking at c. So let's talk about the purpose of scientific notation. Now, scientific notation is really used for one of two purposes. We either want to take very large numbers and write them in shorter terms, or we want to take very small numbers and write them in shorter terms. Let's take an example. The distance to the sun is 93 million miles. That's a fairly large number. Well, we can sit there and write it in a very short, much shorter terms. We can write 93 million as 9.3 times 10 to the 7th miles. Basically what we're going to do is we're going to find our decimal place, which falls way over here at the end of the number, and we're going to take our decimal place and we're going to shift it all the way to the left until there's only one non-zero digit to the left of the decimal. So it's going to be 9.3. With scientific notation, we drop all the zeros that come after it. If all there are zeros to the right, we get rid of them, so this is just 9.3. And if we started our decimal here at the very end, we had to shift it over 1, 2, 3, 4, 5, 6, 7 places. And because I'm shifting to the left, it's a positive 7. So 9.3 times 10 to the 7th. A little bit shorter way of writing 93 million. It would really help if it was, say, 93 billion or 93 trillion. It would really make it a lot shorter. Another example is the size of a typical bacteria cell is 5 microns in length, or 0.00005 meters. The scientific notation for this is 5 times 10 to the negative 6. Again, this time I'm going to take my decimal, I'm going to shift it over, this time I'm going to shift it right, and when I shift right, I decrease the power, or I make it the power negative, more negative. So I'm going to take my decimal and shift over 1, 2, 3, 4, 5, 6 places until I get to the 5, because remember we want one non-zero digit to the left of the decimal, and the only non-zero digit here is 5, so I have to shift to the right of 5. And because I shifted 5 places to the right, this becomes, 6 places to the right, this becomes negative 6. So how can we use this to make our lives easier when we're doing operations? Well, when we do operations using scientific notation, I can multiply things actually very easily. 8 times 10 to the 5th times 7 times 10 to the 4th. Well, when I do this, what I want to do is I want to treat my numbers out front separately than the powers of 10. So my 8 times 7 I'm going to treat separately, and my 10 to the 5th times 10 to the 4th I'm going to treat separately. So I have 8 times 10 to the 5th times 7 times 10 to the 4th, I'm going to take the 8 and the 7 and multiply them together. And then I'm going to multiply that by 10 to the 5th and 10 to the 4th. Well, 8 times 7 is simply 56. And 10 to the 5th and 10 to the 4th is 10 to the 9th. I simply add the exponents. Now, this is almost in scientific notation, but what happened is when I multiplied the 8 and the 7, that gave me 56. Remember, scientific notation requires that you only have one digit to the left of the decimal place. So I need to move my decimal place over. It's after the 6. I need to move it to the left between the 5 and the 6. And when I move it to the left, I increase the power of the exponent. So I'm moving it one space. So this was 56 times 10 to the 9th. This becomes 5.6 times 10 to the 10th power. And if I had to rewrite it, this is 56 billion. Again, 5.6 times 10 to the 10th is a shorter way of simply writing things instead of the 56 billion. We can also do division using scientific notation. 4 times 10 to the 5th divided by 8 times 10 cubed. Again, we're going to split up the numbers out front, my c's, and then my powers I'm going to treat separately. So 4 times 10 to the 5th divided by 8 times 10 cubed. We'll take the 4 divided by 8 and multiply it by 10 to the 5th over 10 cubed. 4 divided by 8 is 1/2, or 0.5. So 0.5 times 10 to the 2nd power. Because we're dividing, we're subtracting our exponents. Again, this is almost perfect scientific notation, but I cannot have nothing to the left of my number. I have to have a non-zero digit to the left of the decimal. So I have to shift my decimal over one place to the right. And when I shift it to the right, I subtract. So 0.5 times 10 squared, I got to take away 1 from the exponent. This becomes 5 times 10 to the 1st. And in standard notation, that's simply 50. Well, obviously 5 times 10 to the 1st is not necessarily much better than 50, so we are going to a lot of times just leave it as 50. Let's look at one last example. It says a drop of oil measures 0.21 cubic centimeters is spilled into a lake. The oil spreads out into a circular shape having a diameter of 20 centimeters, approximate the thickness of the film. We're going to take some different strategies. One of the first things we want to do is make a sketch. And the second thing we want to do is try to apply formulas if we can. If we look at imagine the oil hitting the surface, it's going to spread out evenly all directions. We know the diameter is 20 centimeters, so therefore we know the radius is 10 centimeters. The oil is going to spread out in a circle, but there's going to have a very thin thickness on it. And basically this gives it a cylindrical shape. Remember, a cylinder has a circular top with a height. The height's going to be very minimal in this case, but we are going to be able to calculate the thickness of it. The formula for volume of a cylinder is the volume of the area of the top times its height. Area of the top is a circle, so it's pi r squared times h. So our formula is V equals pi r squared times h. We're told the volume is 0.21 cubic centimeters. We know the radius is 10. So I have 0.21 equals pi times 10 squared times h. 10 squared is 100. So h is 0.21 divided by 100 pi. And here's where you're going to have to use your calculator to sit there and do the math, and you're going to wind up with a nice scientific notation of your height being 6.68 times 10 to the